about Riemann sum, and we use it to compute the area underneath a given function. So let's say that we have the following situation. Function f is given. The function is defined on some interval from a to b, and say we want to compute the area underneath the function f. So before we compute the area itself, let's try to approximate this area, and using three approximating rectangles, and we'll be using the left Riemann sum. So what we do is we divide this interval AB into three subintervals of equal length, and we call the length of each of those delta x. So delta x is going to be b minus a over 3. Delta x is simply the length of each of those. This is delta x, and this is delta x. The length of each of those small subinterval is delta x. So let's call the first point a, x0. The second point would be x1, x2, the next one, and x3, which is the same as b. Now, the first approximating rectangle, because we're using the left Riemann sum, we take the left end point of this small subinterval. So here is the small subinterval, the first one, and then we take the left end point of it because we do the left construction. And then we evaluate this function f at that point x0. So this is exactly the height of this rectangle, and when we multiply it by delta x, by the base, this quantity right here, this is the area of this first rectangle. Then we repeat this construction. Here we consider the second small subinterval that goes from x1 to x2, and because we do the left construction, then we take the left end point, which is x1. Then we evaluate this function f at that point x1, and f of x1 is exactly the height of this small rectangle. When we multiply it by the delta x, by the base, this quantity here is the area of the second rectangle. Then we consider the last small subinterval that goes from x2 to b, and then because we do the left construction, we take the left end point, which is x2. Then we evaluate this function at that point x2, and f of x2 is exactly the height. It's exactly the height of this rectangle. And when we multiply it by delta x, this quantity, this is the area of this third rectangle. The sum of those three would be in a way approximation of this area of interest, and we call this L3. So L, because we do the left construction, this is the left end points, and 3 because we have three approximating rectangles. We can do the same construction with, and we can construct L4. So the only difference would be delta x. In this case, delta x would be b minus a over 4. And then in L4, we'll have 4 of those approximating rectangles. Same construction or similar construction L5, L6, L7, and so on and so forth. And in general, we can do this for Ln. Now, the area of interest, so this is the area underneath the function, would be the limit of the sequence Ln when n goes to infinity. That's the construction of the left Riemann sum. And there's a similar construction. Those are the right Riemann sums. And the difference is that the sample points would be the right end points as opposed to the left one. So let's see how it works when we take just three approximating rectangles. So we split this interval AB into three subintervals of equal length. The length of each of those would be delta x. So this is delta x. The length of this second small subinterval also delta x, and so is the last one. Now we call this point, the first one x0, this is x1, this is x2, and the last one b, which is x3. And then we consider the first approximating rectangle, but then this time, because we do the right construction, this is the first small subinterval that goes from x0 to x1, and because we do the right construction, then we take the right end point, which is x1. Then we evaluate f at this point x1, and f of x1 is exactly the height of this rectangle. Multiply this by delta x, by the base of this rectangle. This quantity here, this is the area of this rectangle. Now we do some similar for the second small subinterval that goes from x1 to x2. Because we do the right construction, then we take the right endpoint, which is x2. Then we evaluate f at that point x2, and f of x2, this is exactly the height of this rectangle. And when we multiply it by delta x, then this quantity here, this is the area of the second rectangle. And we do something similar with the last one. This is the small subinterval that goes from x2 to x3. Because we do the right endpoint, then, well, the right endpoint of this small subinterval is x3. And then we evaluate this function f at that point x3. This is exactly f of x3. Then when we multiply it by delta, that will give me the area of this last rectangle. So this is approximation of this area of interest, and it looks like it's an overestimation because it looks like the approximated area is a little bit more than the actual area, and we call this quantity R3. Because the index 3 is because we have 3 of those approximating rectangles. We can do a similar construction for R4, 5, and in general for n. And when we take the limit of this sequence Rn, this is exactly when n goes to infinity, that will give us exactly the area underneath the function f.